operations, recent developments.
Thank you very much, Krishna. Good morning, ladies and gentlemen. I hope you can hear me. If you can't, please wave your hand. So let me begin by thanking the University of Connecticut and particularly Krishna for giving me the opportunity to talk about something that I'm enthusiastic about, and it's operation of UAV formations. And I'm interested in it from both a scientific point of view and an applications point of view, because I do work with our defence people on matters of unmanned airborne vehicle formations. And as this first slide shows, I'm reporting work done with a number of people, and here are their pictures. And I'm going to begin with a few high-level remarks on 2 slides. The major use for UAVs with which I've been associated is localization. That is, figuring out where a target is. A target's not necessarily something you're shooting at, it's maybe a person you're rescuing. And many target localization technologies require multiple measurements concerning the target, and typically from different positions in space, because you're using direction or time difference of arrival or something like that as part of your localization technology. And if the target's stationary, you might be able to get multiple measurements with a single vehicle moving around, but the target may not be stationary, and that might take you a while. So having a bunch of vehicles is a good idea. And often a vehicle mightn't be big enough to put a number of sensors on it. So if the vehicles are small, you really have to have multiple vehicles rather than more sensors on those vehicles. In addition, with small vehicles, and these are the sort we work with, you may be restricted in the sorts of sensing technologies you can use. For example, you might not be allowed to broadcast. If they're small, you can't get a physical spread of any antenna. And for some vehicles, there's a very real payload restriction, and I'll show you a picture of a couple of vehicles there in a moment. So these all drive you towards using unmanned airborne vehicles in formations, and Australian defence people use a particular form of vehicle called an aerosonde. I'll show you a picture in a second, which is pretty cheap. And maybe soldiers in the American Army or the Australian Army in 10 years will be searching a building using micro airborne vehicles. Another general remark is, I'm aware the US has these things called Global Hawks, and I believe they cost about $100 million. And that's a lot of money in a single vehicle, of course. And from some points of view, just having some plain, cheaper vehicles organised into a team may be a better bet. It's certainly a cheaper bet, because some of these vehicles only cost $50,000 each. And if you have, though, a team, you've got to coordinate it. And so all these sorts of questions come up. Who measures what? Who communicates to whom? Who tells who what to do to move the formation as a gross entity in some direction, or to change its shape? Is there a leader or isn't there a leader? What happens if you lose a communication link or you encounter a GPS denial situation? And how do you manage external command and control? So having said it would be a good idea to use a formation, a whole lot of questions present themselves on the table. There's scientific questions that are underpinned by typically sensor or more generally technological constraints, and there'll be a version of the questions applicable if you're working in the sea also. I think of them as mixed control and networking questions. The networking side includes communication, and graph theory in the mathematical sense of the term is an important underpinning tool. So these are my high-level remarks. Just to look at a couple of pictures of UAVs, here's an aerosonde vehicle. It costs about $50,000. It can travel at about 80 knots. It can cross the Atlantic. It can fly for 24 hours without refueling. It's far too light to have any weapons. The payload is between, I think, 1 and 2 kilograms, which means you can't afford to just load it up with too many sensors. Here's another UAV sitting on a 1-cent piece, and that might be the size of micro-airborne vehicles which in the future could search a building. Again, you could see you could hardly load that vehicle up with a bunch of sophisticated sensors. It's a pretty small vehicle. So I've commented here, firemen may search a burning building with this sort of vehicle. Okay, so the main driver for me, though, has been the aerosonde vehicles and the problems these have posed to the defence people. As I've said, a big application is localisation. And in order to localise, they will typically have formations which are regular. It turns out, based on Kramer-Rao considerations, a regular formation may be a good idea. And if you just had 3 vehicles, you might have, for example, an equilateral triangle with a distance between the vehicles of 2 kilometres. So the vehicle wingspans may be 2 metres, so these vehicles are pretty widely spaced. It's not like a school of fish where you've got to worry about the fish bumping into one another. And we're not talking about hundreds of vehicles, we're talking about 3 or 6 when we're talking about the aerosondes. So there are 2 key separate tasks that you can identify in this situation. One is formation shape control. That is making sure that you've got an equilateral triangle, or you form it and it stays as an equilateral triangle. And the other is moving it from A to B, or searching an area or something while maintaining the shape. And that's known as velocity consensus, a technical way of saying, well, all 3 vehicles have to have the same velocity if you're going to maintain the shape, because if they get the speeds wrong or the directions are inconsistent, you can't maintain the shape, obviously. So you need shape control and you need velocity consensus, and they're logically distinct objectives, and with both of those you can move a formation round. Now, these agents are flying around the sky not just to look at one another. Primarily they're looking at targets that may be on the ground, but in order to maintain a formation shape, they're going to need some kind of sensors to determine where their neighbours are in the formation. Now, if it's just 3 agents, each has got 2 neighbours and that's it. So neighbours not a very complicated concept. And one of the rules of the game here is you're not allowed to rely on GPS. It's often not available. If you're searching a building you're inside, it's maybe not available. So all this has got to be done with minimal assumptions about availability of GPS. And agents, besides being able to sense targets, need to be able to sense their neighbours when they're moving as part of a formation or determining a certain shape. And sensors to assist in moving are indirectly useful. And so if you could dispense with them, this would be good. And you might want to dispense with them because payloads are really so limited. Remember those 2 pictures I showed you of the 2-metre wingspan aerosonde and the 1 US cent piece micro-airborne vehicle. So the key question is, how can we economise on sensors used for these motion tasks? By motion tasks I mean getting a certain shape and translating as a rigid shape that is achieving velocity consensus among the agents. How can we economise on sensors? And then we can then use sensors to if there is payload space, look for ground targets. So I now want to talk in a bit more detail about these 2 tasks associated with motion. One is formation shape control, and the other is velocity consensus, and give you a little bit of a feel for how how these things can work. So let's assume to begin with that we're just interested in a triangle, and we specify 3 interagent desired distances like 2 kilometres, 2 kilometres and 2 kilometres. So you might imagine that each agent could sense the actual distance to its neighbours and compare the actual to the desired distance and move to correct the error. And let's suppose that we're supposed to be 5 metres apart, and I sense that we're 4 metres apart, so I've got to correct by 1 metre. Then I need to move further away, and in order to move further away, I need to know a direction as well. It's not good enough just to know the absolute value of the distance error, because it's going to be hard to correct unless I know which direction. So typically the motion to correct the error has to be, in the first instance anyway, along the line joining the 2 agents, which means I need to be able to sense not just the distance from the agent from which I'm supposed to maintain 5 metres or 2 kilometres. I need to know, for the purposes of correcting that distance, their bearing. That is, I need to know the relative position of the agent. So just to show you what you can, I'll put a law in a little while on the screen, but I want to show you what you can do with this sort of thinking. This is a triangle, and it's supposed to take up a certain position. And when you implement a standard sort of a law, the triangle will take up a certain position and come stationary. And I'll show you a law in a minute, or tell you about the laws anyway. Here's a more complicated formation. There's 4 agents, and there's 6 interagent distances that are supposed to be maintained. And you program this thing, and you get this sort of motion towards desired spacing. Now that's an academic example. The spacing doesn't mean anything, but it just shows you that the scheme of correcting desired distances makes sense. So just a little more detail about how this works. Each agent senses the actual distances to the neighbours, compares it to the desired distance, moves to correct the error, and it moves along the line joining the 2 agents. And the way you can set that up mathematically is to form a cost function, and the cost function compares the desired distance between agents I and j with the current distance between agents I and j, creates an error. The error involves the square of the distances, and then it sums up all those errors, and this is called a potential function. Yes?
Can I ask you just a very simple clarification question? I'm trying to understand now. If you have a triangle shape, there is no problem. So every agent is looking at 2 other agents. If you have this quadrant,
Yes.
all of a sudden by describing what the distances will be, aren't we violating the decentralization of the control? It is true that in the quadrilateral I showed you, it was a complete graph. But we could have had a situation where I didn't specify this distance. I just didn't choose to show that. And in that case, this agent doesn't have to worry about the one right over there. So there's an extensive theory that says how many edges you have to maintain the distance of given n agents in order to maintain what's called rigidity of the formation. And the theory delivers the result that the number of edges that has to be maintained is linearly proportional to the number of agents, whereas the potential number of edges is order n squared, half times n minus e. That I understand.
Yeah.
However, for example, this quadrangle,
Yep.
I would like to specify the shape,
Yes.
and then let the agents determine which corner they're going to go at, which node they will be at. So that's the total autonomy.
This is not meant to be a map of where the agents are supposed to end up. It's meant to illustrate the formation with the centroid and the orientation being irrelevant, and it's meant to say that there's an agent here and there's an agent here, and they're trying to maintain a prescribed distance. They're given a list of distances. They're not trying to get
to Stores, Connecticut or New Haven. Is that cleared up?
That's there.
Yeah. Yeah.
For example, do you always get to that desired state, no matter where you start from with the Fourier transform?
Just about, and I'll say a bit more with these
That,
diagrams.
if that does it, then it answers this
Yeah,
question.
yeah. So that's the potential function, and if you move along the negative, if you set up what's called a negative gradient flow or a gradient flow that moves you along in the direction of the negative of the gradient, then you'll go to an equilibrium of that potential function, and so there's a question of are there local minima and global minima, and for some sort of graphs there is a global minima and a global minimum, and certainly there is for a triangle and even a double triangle. And this, you get a nonlinear, you do have a decentralized law here, because in this decentralized law, what you've got is a sensing of the neighbour agents of agent I governing the motion of agent I. So agent I needs to know the relative position, Pi minus Pj, for its neighbour agents. This is the ones where there is an edge in the associated graphical picture. And then it's also multiplied by the error between the square of the current distance and the square of the desired distance. So the motion of this thing is the sum of a motion to correct the errors in the distances to each of its neighbours. And each of those components is along the line joining it to those neighbours. So, but some funny things can happen. For example, supposing I specified 3 desired distances and they didn't satisfy the triangle inequality. So what happens there, I'm just showing you this as a kind of sidelines, not terribly important for this talk. So you do converge still, but of course you can't converge to the correct distances, and you end up converging to a straight line, which you might have intuitively thought. Here's another example. Each of the agents is measuring the distances to its neighbours, and maybe I think we're 10 metres apart and he thinks we're 9.5 metres apart, so there's an inconsistency in the measurements. Or maybe we have a bias in our sensor. And so what happens if you get inconsistency in the measurements, and I do know that my good friend Steve Morse did talk about this. So you converge quite fast to a correct triangle, but it's not stationary. It floats around maybe in a very big circle in space. Now the next one I'm showing you is a plot associated with some real agents where you're worrying about wind and noise in the distance measurements, and very importantly, these agents are like aerosonde, these aerosonde agents, and they happen to have very little speed control. They've got orientation control, but roughly speaking, once you put one of those aerosondes up in the air, it's constant airspeed. So they're supposed to be the same speed, but that's a nominal thing, and this plot shows the case where the 3 agents have close but differing fixed speeds, and they're pushed around by wind in the air, and there's errors, and they're supposed to trace a sort of a spiral. So you can see they are in fact tracing a spiral, and what happens is that the slowest agent, as it turns out, has a smoother track, and the fastest agent has a more wiggly track, so that the net progression in the desired direction becomes the same. So that's a sort of more practical agent model. Now what about velocity consensus? Let me show you what this is. We're temporarily not worrying about shape for the moment. We've got 4 agents here, and we want them all to acquire the same velocity by looking at their neighbours. And what you'll see when I run the graph is that some of them start off much slower than the others, but they all end up with the same velocity, and so they're parallel. So the bottom one's much slower than the left and the right, but it's gradually getting faster. And so by this stage, they were all more or less maintaining the same velocity. So we've got velocity consensus. And how does that work? Velocity consensus algorithm's very simple. You just look at your neighbours and move towards the average of your velocity and your neighbour's velocity. So if you express that, it's just a linear differential equation. And the words your neighbours are summed up in J is in Ni, because Ni is the set of neighbour agents of agent I. So this is the discrepancy between your velocity and that of agent J, J being one of your neighbours, and you add up, you multiply all those discrepancies by some negative constant, and it gives you your acceleration, and as a result of that, everybody ends up with the same velocity. And again, the law is decentralised because you are just looking at your neighbour agents. And to operate this law, you need measurement of your neighbours' velocities. And as it turns out, you can combine a velocity consensus and a shape control in a single algorithm if you want. And you can also, especially for velocity consensus, designate one agent as the leader, and so all the other agents have to acquire the leader's velocity, which is an obvious sort of a reasonable thing to do.
Is it done distributed way or?
Say again?
The leader.
What was the question?
Is the leader known beforehand? Or?
The leader has to be known to all agents. The leader has to be known to itself and its neighbour agents beforehand. And so supplementary questions come, what do you do if you need to change the leader, or, you know, the leader has a heart attack or something? So to do shape control, as I've explained it, or to do velocity, and velocity is just a derivative of the position, then you need range and direction of your neighbours, and that's potentially expensive if we want to cut down on the number of sensors on our vehicles. So the question is, can we dispense with some of the measurements that are presumed to be made in those algorithms that I've just talked to you about? And so the next part of the seminar is talking about how we can dispense with some of those measurements. So you can simplify the problem down and just ask about two agents. Well, if you've got two agents and you measure a distance to a neighbour, how can you localise it? How can you learn its velocity? That's the problem. And again, I want to hit the GPS thing on the head because it's kind of irrelevant. Our defence people say you're not allowed to work with GPS because there's issues of denial and loss of signals and so on. So we rule GPS out of the picture. Or you might say, if you can measure the bearing to a neighbour but you can't measure the distance, same problem arises. And I just want to say again, nearly all the solutions to the problems that I've posed assume that you can measure range and bearing, that is relative position of your neighbours. And again, payload restrictions or radio silence requirements or something may limit your sensing technology. So this is the issue we're looking at. So now I want to talk to you about how you can do these sort of things just with distance-only measurements. And that might be a little bit of a surprise, but you can. So one suggestion that was in the literature actually of sensor networks was that you randomly vibrate the agents, but that's a bit tricky to consider in this context, and I'm not going to consider it further.
Almost
It is like a dither signal. But you'll see later on we do something that's, I suppose, a first cousin or second cousin of that, but we don't actually put white noise or something like that on the agents. So the high level, there is a high level principle governing what we do. These vehicles do have inertial navigation on them, and the high level principle is that each agent makes some planned motions that use parameters that it knows, but maybe its neighbour doesn't know. But its neighbour's doing these planned motions also, and in collecting distance measurements or bearing measurements, but not both, over a time interval, we're able to work out, if we've collected distance measurements, what the bearing is, or if we're collecting bearing measurements, figure out what the distance is to the other vehicle. So it says the idea is to use the distance data to B, collected at A, and collected over a time interval to infer the bearing of B at the end of the interval. That's the very high level statement. And a lower level aspect of this is that A doesn't know what B's motion is exactly. It knows something about its character. For example, it may know that B's doing a circle or that B's doing some straight lines, but it wouldn't necessarily know the parameters. And again, another high-level statement, it turns out, this is looking ahead, that if you can do this sort of stuff in order to get shape control, it's not much harder to do it to handle velocity consensus, where you require derivatives of position, relative position rather than relative position itself. So there was some work on straight line movements. That's several years old now. And the trouble with straight line movements is that the agents can get a long way away from one another, and you can destroy the notion of the formation, so that's a bit unsatisfactory. So to sum up, there was the straight line thing where the agents did this sort of movement, and then there was the random vibration thing where they did this sort of movement. And what we're going to do is look at circular movement instead, and we'll see that this works either if you use distance-only measurements or bearing-only measurements. So how does the bearing one work? So let's think of a primitive problem where we've just got two agents, and they're each have their motion at this stage confined to a circle. There's no general translation. And one agent measures the bearing of the other agent, and the task is for that agent to infer the position of the other agent using bearing measurements over an interval. So if you make this a little more precise, agent 1 knows its radius, its angular velocity, and its phase, and it measures theta of t, and it's got to determine the angular velocity, radius, and the circle centre and phase of agent 2. And it does not have available the distance, z of t, between itself and agent 2. So you can write down some simple geometric equations, obviously, and you can rearrange them, and you get a thing like this. And in this equation, everything on the left-hand side is known, and the unknowns are on the right-hand side. So the unknowns are omega 2, phi 2, r2, x2, and y2, and the known stuff is what's over there. Now, figuring out unknowns in an equation like that, where some of them are rising linearly and others are frequency, is kind of a sort of thing signal processing people are used to doing. And so you can do it, and I'm just going to make a few remarks about it. First,
You can argue that the bearing angle function theta of t is an almost periodic function. That is, it's expressible really as a sum of sinusoids, cosines and sines. And so you can collect theta of t over an interval and take its Fourier transform, and you'll see this sort of picture for theta of t, and unsurprisingly you see some frequencies and difference frequencies sitting in there. So the first thing that happens is that using the measurements of theta of t, you sort out frequencies. And so that's effectively done with Fourier analysis. And once you've sorted out what omega 2 is, these other parameters, y2, x2 and r2, that's the centre of the other agent's orbit, that's the radius of the other agent's orbit, and phi2, the phase, those can all be obtained easily from that equation because effectively they occur linearly. But, and that means that agent 1 localises agent 2. Now I've smoothed over a few difficulties and I just want to refer to a couple of them. First is theta t, and then there's a second difficulty associated with the frequencies. The difficulty with the theta t is that there's noise in this thing, and so you put some noise on theta and recognise that tan theta can be infinite. You can get gigantic errors in tan theta of t for quite modest errors in theta of t. So that's bad news. The values of tan theta may be very large, and then noise is a very real menace. So this will break down in large noise. The other thing is... I'm sorry, I couldn't hear.
Instead of using least squares criterion, we have used one norm error, right? That tends to be the
Yeah, you could. We didn't try that. There's an intrinsic problem though if theta's close to 90 degrees, and the way we've dealt with that is a kind of a resetting thing where you move it down to near 0 degrees.
I had a question: is this an observable problem?
It is an observable problem. Yeah.
Actually, you said it's observable. I can see it's observable for bearings only, but it doesn't look like it's observable for range only.
I'll show you that I'll show you that in a second. Yeah. So it's not always observable either. The frequencies need to be different. If omega 1 minus omega 2 happens to be 0, then you're confusing a difference frequency with a DC frequency, for example. So there are certain patterns of frequencies for which you'll have a problem. Another issue is, why should you have to fly in a circle to localise? Isn't this kind of wasteful? And as you'll see later in some simulations, if overall I'm moving in this direction and I superimpose a circular motion on the linear motion, then I just put a wiggle on this trajectory, and it's nowhere near as wasteful. So the distance-only stuff is pretty much the same, and remember we're wanting to do formation, shape control and velocity consensus and eliminate some senses. So the picture that we're looking at is this one where theta of t is no longer available. We've got the same types of motion, but z of t is what we can measure rather than theta of t. So z of t's got the blue circle. So what we're trying to determine, though, and what agent 1 knows is the same as before. So if you write down what z or z squared is, there's a picture of a z squared, and z squared is a finite collection, a finite sum of sinusoidal terms with various unknowns popping up around the place. But omega 2 is the key unknown that's arising non-linearly. So there's only a finite number of frequencies there. So provided that you don't have things like omega 1 minus omega 2 equals 0, or omega 1 minus omega 2 is, well, maybe there's some other awkward values, then you'll be able to sort out what the frequency is with a Fourier analysis. and then once you've sorted out the frequency, you can work out the other parameters. So here's a picture of the Fourier transform of the square of the distance up the top, the magnitude, and the magnitude up the top and the phase down the bottom. And the amplitudes of the different components yield the unknowns in the expression for z squared, and as a result, yield for you everything you need to know to localise, sitting in agent 1, the position of agent 2. But bad frequencies are possible in the same manner as they were for bearing only.
How do you know whether some frequency is negative or positive? You already know that.
Yes, no, I understand the question, and I can't remember the answer. I know we did address that question, and we also considered for a whole formation, how could you choose frequencies so that you were not going to get any embarrassments from omega 1 equals omega 2, and if you know that each agent has at most 3 neighbours, I think, or there's some rule like the maximum number of neighbours determines the total number of frequency values that would be required for the whole formation. So there is more detail, and I'm sorry, I just don't remember it. So I've talked about localization using distance measurements or frequency only measurements. Yes, question.
Given the degrees of freedom of each agent, what's the practicality of having these circular motions, which are sort of local motions, global path?
I'm not sure I heard all the question because I am a bit deaf. So you have to speak a bit louder. But I think you said, what's the practicality of
given the degrees of freedom of each agent,
yes,
and given that this circular motion is some sort of local motion compared to the global path?
Yes. Look, I'll show you some curves in a moment, and what we're talking about is a small variation on a translational path, and that's all. So it's not a big issue. So ask the question if you're not satisfied with the later pictures, or re-ask it. Yeah. So to say something about velocity consensus, you can do this for distance only or bearing only, but if you've got different velocities and this agent 2 is moving relative to agent 1, so its relative velocity has got 2 coordinates, Vx and Vy, then the x component of the relative position 2 relative to 1 will change like this, and the y component will change like this due to the motion. So if you write down the equation for z, it's this thing up the top here, and z squared still has 3 sinusoids. It's just that the coefficients of the sinusoids are polynomial in t. Now, if you know stuff about Fourier transforms, you know you've still got the same frequencies. Polynomials make it a bit more complicated, but you don't get extra frequencies by having polynomials replacing constant amplitudes. So you've got to sort out the fact that the amplitudes are varying, but you can still get omega 2 in the first instance, and then things are pretty straightforward, and so you can obtain the relative translational velocity between the circle centres and localise the agent as well. So a little more detail now about achieving velocity consensus. We'll assume each agent collects distance information from its neighbours over a time which we'll call a sampling interval, cap t, and it doesn't change its velocity in that time. It uses that information to localise and estimate its neighbours' translational velocities, and then it makes a step adjustment to its own velocity rather than a continuous adjustment, and it makes that step adjustment every capital T seconds. It gets the data and then it makes a step adjustment, and this is just actually a discretized version of the earlier velocity consensus equation. So I'll run the simulation and then show you what the tracks look like. And this is not the final simulation that I want to show you. This is a velocity consensus, no shape control at this point. And it's a velocity consensus that uses distance-only measurements. And each of these three agents is starting with a different velocity, and they're just making circles and measuring distance to their neighbours, and they're learning and acquiring a common velocity. Agent 2 is interchanging information with both 3 and 1, but 1's only interchanging information with 2, and 3's only interchanging with 2. So it's just going to do that up to the top of the page. So that's the trajectories. It's not the last trajectories that I'll show you. So there's still perhaps somewhat wasteful.
Is there a prescribed formation in this case, or just the velocity consensus?
This is just velocity. And this is a picture just showing all the velocities come into synchronism in the x direction and the y direction. So you can see there's a lot of circling with little benefit once you've achieved consensus, and it is pretty accurate, but there's high energy consumption. So we have an idea, which is to lower the amount of circling once you've done a good job with the consensus by making something adaptive. And so here's a kind of adaptive, a basis for an adaptive rule. I won't give you more details on it. And here's a simulation.
This seems to be similar to what happens with gradient type algorithm. That's what the stuff is.
I'm sorry, I can't hear.
It's almost like a steepest descent type of thing. That's the reason why you're getting this zigzagging.
Yes, I suppose
So
it.
why
that's right.
couldn't you use some of the techniques they use in terms of the conjugate gradient type of thing? Can you do like a momentum and
Well,
kind of thing that people use?
Maybe, but there's a thing I haven't talked about here, which is that there's a turning radius constraint. And so you've got to focus on any radius, or you've got to focus on the curvature that you're using. And if you're translating and circling, the curvature isn't just the radius of the circle. So behind all this is incorporating the turning radius constraint, and it's straightforward to incorporate it with this adaptive algorithm. So that shows that you can sort of switch off the wastefulness once you've acquired a consensus. And I think I've got one which shows, yes. So wind or change of direction by the leader or something may break consensus. And so you need to be able to re-achieve consensus. And here's a picture of the circling thing being largely turned off, and then consensus is broken through change by the leader, and that is sensed, and so there's some more circling until the new velocity is learnt by the other two leaders, and then off they go to the left-hand side. Okay, so I'm getting near the end now. I want to show you how you can combine shape control and velocity consensus using distance-only measurements. And again, you can do this with bearing only because it's all using this localization trick. So, not many equations, but here they are again. This was the shape control algorithm with no velocity consensus, and it involves the first derivative of pi, the position of agent I. And on the right-hand side, you've got relative positions pi minus pj, and distance errors measured in a certain way, errors between the actual squared distance and the square of the desired distance. And the velocity algorithm was simply accelerate or decelerate to bring your velocity nearer that of your neighbours. And magically, you can just combine these two into a second order equation, and this equation provably will give you a velocity consensus plus a shape control. The right-hand side of this equation has just got the bit from here and the bit from here. The left-hand side has got the second derivative, which is there, but not the first derivative, which was up there. So it's a kind of magic that this equation can do both. That's fine if you have instantaneous distance and bearing measurement and everything, but if we've got to do this estimation trick, we need a discrete time equation which adjusts things every t seconds. So we collect information for time t and then reanalyze where everything is, and so we use that equation in a discretized form, and you can prove an exponential convergence property for that equation. So a couple of fairly technical remarks, but I don't want to submerge you in too much detail. The algorithm is a gradient algorithm in continuous time, and there's actually a lot of theory about convergence of gradient algorithms. To study the details of that algorithm, you need a tool called center manifold theory. And once you discretize, the whole question arises, well, will the discretized equation really capture the same sort of phenomena that the continuous time equation captures? Will it be a gradient algorithm? Is there a center manifold theory for discrete time equations that delivers you exponentially fast convergence and so on? And the answer to whether you can discretize this is, I think, an open question, but there was a predecessor to center manifold theory, a Russian called Malkin, which is now regarded as a simplification of center manifold theory, but you can discretize his theorems, take a theorem for a continuous time system and just say, well, we make the discrete time equivalent, and you retain his conclusions. So that's the basis of the proof that we used, that this algorithm is theoretically justified. So I'm going to skip that. So this, I think, is a just absolutely beautiful picture because it shows simultaneous shape control and velocity consensus. I don't have a movie of it. The idea is to form a triangle, and you can see you've got a lovely triangle up the top, and the thing's probably formed a triangle there, and off it goes. So these people can just measure the distance to their neighbours, and they do some circling here and learn something about the positions. They start off with different velocities. They learn the velocities of their neighbours. They tune the velocities, and they form an equilateral triangle, and off they go to Boston or something. It's, I think, just a beautiful picture. So if you're not as enthusiastic as me, I apologise for overstating my enthusiasm. And there's a picture of the way the velocities are coming into synchronism. So to draw a few conclusions, the first is that shape control and velocity consensus are two key functionalities that you need for formation control, and most people would say that to use those in a real system you need position and bearing measurements, and what I've argued is that that's not so. You can use position measurements or bearing measurements, at least if you've got inertial navigation systems on board, as certainly the Aerosonde vehicles do. And you can do shape control and velocity consensus simultaneously. An open question is, what if the agent speeds are fixed if they're 30, 31 and 32 metres per second and there's wind round? What are you going to do? Because in these algorithms we haven't imposed a restriction that the only thing you can adjust is direction and you can't adjust airspeed. But we've certainly got some ideas on that question. And it's important to answer that question for this algorithm to be usable with the Aerosonde vehicles. And the defence people would love to put more sensors on the Aerosonde vehicles that could look at the target data and so have less sensors for dealing with the formation control. Another question is, can one continuously update the localization measurements? You would think so. The demodulation of frequency modulated or phase modulated signals using a phase lock loop is a system in which online you're estimating omega 2 and phi 2 really, but along of course with in this problem you've got the frequencies arising in the measurement in an unusual way, and you've got parameters occurring linearly. But probably some idea based on phase lock loops will enable you to do the estimation continuously rather than blocks of time, t seconds, where you run an FFT. So if your sensors, if your UAVs are outside rather than in a building, there's likely to be wind, they may well be vibrated by the wind, there's random motion. You'd ask the question, can you exploit that random motion to improve the accuracy of obtaining the missing data? Because it was random motion that is behind the work on sensor networks where you consider random vibration of the nodes. And then finally, all those equations I showed you, they didn't have noise in them and they didn't have bias in them, and they're nonlinear equations. So you could ask the question, how do you model noise and bias more effectively in the equations? Of course, you can put noise and bias into simulations and say, well, this is what we found with the signal to noise ratio of whatever in the distance measurements, we got this sort of performance. But it would be nice to be able to also look at it analytically. So I'm very happy to take some questions if there's time, Krishna.
So if I may continue on the
Major from mechanical.
window research. Sure. So I'll follow up on the understanding is that for a triangle shape formation, I understand fully. But if there are more agents, now we will have to wrap up the topography somehow. The topology is complete graph. Is that correct?
No, it doesn't have to be a complete. It doesn't have to be a complete graph.
It's not. It doesn't have to be a complete graph, but form in some sort of triangular form that are building up to complete the entire topology.
Let me. I know I'm interrupting.